Okay, good morning, everybody. Very good morning, actually. So Garrett and I just got back from the joint math meetings, and we had the best time ever. So we met Dr. Vakil, you know, uh, and he was the nicest guy ever. Just like great, 10 out of 10, super nice guy. And so he asked us about kind of how we were liking the book and where we were at and stuff. And we talked to him about the base change diagram of pain and suffering. And yeah, so he asked us, we were saying like, oh well, you should include like the full base change diagram, somewhere, maybe in an appendix, just so that people have a reference to make sure that they're doing it right. Um, And he was like, "Oh, well, that's good advice. Like I'll think about that for the next edition. I'm just curious, like how long did it take you guys to do it?" And we were like, "Oh, like about 2 hours." And he was like, "Oh my gosh, 2 hours? You know, that's way faster, than I thought it was going to take. I can't make it easier now." Um, and so that just about made my life. So anyway, and then he signed my book. Which meant just a ton to me. So anyway, I thought I would brag about that because that was like the best experience ever. Um, anyway, on to the actual topic of today. Um, so we are finishing up um, three, and since it's been about a week, let's just kind of see where we left off. So we left off at the radical ideal. Um, and I think, yeah, so now, all right. What we're going to do is we're going to state a theorem that basically radicals commute with finite intersection. Um, and kind of the formalization is that I1 through IN um, in our ideals, um, then the radical of the intersection is equal to the intersection of each radical. Um, and so quite simply, we'll do a set containment proof, so direction one. Um, you know, we can, should be yeah, let R in the left-hand side. Well, this is all of the R prime in R such that R prime to the N are in the intersection for some, and I guess I should say K. Right. Um, well then, I guess let's compute the intersection just so that we have it. It's equal to the intersection, I equals 1 to N of R prime and R such that r prime to the k is in I for some k. Um, and so then this r that we've distinguished, then r um, has k and z for every I such that r is in, or such that r to the k is in I, right? And so left-hand containment follows. And then alternatively, let R be in the intersection. Then the tough part is that we need to show that hold on. Then there exists k such that r to the k is in the intersection I equals 1 to n of I. But the intersection of is contained within I for all I. And so then wait, no, I did this wrong. That's why it doesn't make sense. So there exists this thing, k, such that r to the k is in I, and this time it's a ki, such that r to the ki is in I for all I. Oh no, but this is a shared k. That's the whole point of this, is that it is a shared k. But then so r to the k is in the intersection of I. And I think that that completes the proof. Does that make sense, Garrett?
Yes, it does.
Okay. Yeah, so then we have a theorem. Um, the radical ideal I is the intersection of all prime ideals containing I. Um, 3.2.13. Yeah, so the null radical is the intersection of all prime ideals of A, and so then this is a subset of the. No, this is a superset of the null radical. Yeah, that makes sense. Okay. Um, so yeah, proof sketch here is that the nil radical on R is a subset of root I, since this is intersection of all prime ideals. Um, and then this corresponds to vanishing on spec. But then this corresponds to vanishing on I, which corresponds to prime containing I. Anyway, does that make sense?
Yes. Can you just give me a second to get it down?
Yeah, I'm just gonna blow my nose real quick.
Okay.
Okay. You ready?
Yep.
Yeah. So as an example, um, so as a set, complex affine space was just traditional points, corresponding to maximal ideals, and then one new point, which was 0, right? Prime ideals and 0. The Zariski topology on this is not exciting. The open sets are the empty set and A1C minus a finite number of maximal ideals. So under Zariski, sets are empty set and then minus finite number of prime ideals. Um, no, maximal ideals. Um, Open sets are determined by their intersections with traditional points. The new point, 0, comes along for the ride, which is a good sign that it's harmless. Ignoring the new point, observe that the topology on A1C is coarser than the classical topology on C. So coarser meaning that it has fewer things. The picture that I learned in topology, so there's coarser and finer topologies. A coarser topology, it's kind of like a bundle of rocks. A
Okay.
coarser bundle of rocks means the rocks are bigger, and so you have
Yeah.
fewer of them.
Okay.
Whereas a finer bundle of rocks is like you have more rocks that are smaller.
Yeah,
Um,
that makes sense.
so that's how I always remember it.
Yeah, that's a good way.
So I don't really know how to classify this. So the topology on the affine K line would be that open sets and then does that seem right?
Yes. Hang on, let me just think through it.
Okay.
Yeah, that works.
Okay. So we know that Spec has, all of the x minus a's, all of the y minus b's, and then we have the x minus a, y minus b's. I think that's it. And I guess actually what Vakil does is it doesn't have to be quadratic, and so in the zero ideal. So then the closed subsets are the entire space n0 um a finite number of curves and a finite number of zero-dimensional points. Yeah. And the
Of what type
geometry
of points?
here,
I'm sorry.
zero-dimensional, so like x minus a.
What's a VV?
Vice versa. Sorry.
Okay.
And I guess rather, this is the zero set. So this makes a lot of sense. So phi from B to A induces pi from spec A to spec B, and this is a contravariant functor.
What's the Yoda embedding?
Yeah, well, that's the unique determination functor, right?
I was just saying it's contravariant.
Oh,
That
yeah.
is.
Yeah. Yeah. This reminds me, I need to send the receipts to the math department.
uh, you don't
I
do
don't
that
think.
like in the when we go back to school.
Well, I need to have money back I paid out of
That's true.
pocket.
Is there a way to do it?
So,
Cause yeah, but like, is there a way to do it? Cause like I have like that physical parking ticket.
yeah, but I have all of the
Oh, you have your stuff online?
Yeah.
Okay. I was just saying it'd be nice to get it back now, but if I only have a physical copy, I didn't know how I could send it in early.
Actually,
Could you explain the intuition behind this?
I'm trying to figure that out myself.
Okay.
So we have, so this is phi, this is pi, and then we want to say that the spec functor is contravariant from rings to topology. So we want to let I be closed in spec B. Want to show that pi inverse of spec, or pi inverse of I, is closed in spec A. Um, and then as a functor, I'm just gonna do like a cursive S, right? So we can take, um, the inverse functoriality of I is closed in B because that's how functors work. But then phi of S inverse of I is closed in A because that's how morphisms work. But then S of phi of S inverse of I should be closed in spec A. And this is exactly pi inverse of A. Does that make sense?
Yeah, let me just get it down. Okay. Um, yeah, that makes sense.
Not all continuous maps arise this way, like piecewise functions don't work like this, but
Right.
polynomials work this way.
Yeah.
Um, yeah. So theorem, um, let I and S contain in B, um, be an ideal and a multiplicative subset. Um, then spec of B mod I is a naturally closed subset of spec B. Um, then if S is equal to 1 f squared, um, then spec S inverse of B is open in spec B. Um, um, arbitrary S is neither open or closed. And then the Zariski topology on spec B mod I is the subspace topology induced by inclusion in spec B. Okay, so let's do a lot of proofs here. They're all pretty short though. They're all kind of like one line things, I think. Right, so for for A,
Hang on, you mind
we
waiting 1 second? I just gotta get down the rest of the day. All right.
so if this is phi and this is pi, um then it's natural that these things get sent to each other.
Yeah.
Right? So like B mod I is definitely closed in B, right? And so then that gets mapped to spec B mod I. And so closed sets
Yep.
get mapped to closed sets. Namely, the entirety of spec B mod I gets mapped to a closed set, right? And then for part B, um, we're looking at all of the functions in B which do not have anything in S. And so this does definitely look like an open set. Um, so Yeah. I mean, it's like spec S inverse B is equal to the union for I and I of Fi inverse B, right? And each one of those is open.
Yeah.
Um, and then unions of opens are open. And then in the case of C, um, spec Q in terms of its relation to spec Z. Well, I mean, this is just the fraction field of Z, but it's not open. Like it's not open or closed.
Yeah.
Um, yeah. And then for D, so the subspace topology um, is of like of A contained in B has that open sets are subsets of A intersected with open sets in B. Right, so any subset of A intersected with open sets in B. And so then spec B mod I is literally just, yeah, the open sets in
Yeah.
spec B, but I, so that's just like by definition. So
Yeah.
that's this is a pretty easy exercise, I think. Um, Although I feel weird because his hint was to compare closed subsets, so maybe I'm doing that wrong. Um, yeah. Uh, Remark if I is contained in the no radical, then spec B mod I spec B is a homeomorphism. Um, Useful exercise for later. Um, so if I is contained in B, um, F vanishes on V of I, which is the set of P in spec B such that um, I is contained in P. Um, if and only if F is in the radical of I. And I think the proof of this comes back to um, this thing.
Yeah.
Yeah. And how that relates to vanishing on I. Um, yeah. And then easy exercise that I guess I'll state as a theorem is that Spec K over X localized at X is just spec K. That makes sense.
Yes.
Okay. So I think we should take like a 5 minute break, get some water, and then see what we can finish up. I think we could maybe even get to the end of 3.6 today.
Okay.
Um, so yeah, I don't know. What time do you have to go?
Just whenever.
Oh, okay. Then let's try and finish off chapter 3 today. Like it's all pretty easy.
Okay.
Um, I was reading through it yesterday and I was like, oh wow, we should be able to like breeze through chapters 3 and a little bit of 4.
Yeah.
So yeah,
Okay.
cool. All right. Be back at 8 Give me just 1 second. I just need to finish something up real quick.
Sounds good.
Okay, sorry for the delay. Just had to take care of some stuff. Um,
No problem.
I realized I want to TA abstract algebra this semester, and then I also want to do an honors option for all of my classes.
Huh.
But I haven't actually sent out the emails to like, you know, be like, hey, can I?
Yeah.
Okay. Um, Yeah. On to section. Wow, that was a terrible section symbol. There we go. That's still not that much better. 3.5. So, we're going to define a distinguished open set. So, if F is in A, the distinguished open set, D of F is the set of all P in spec A such that F is not in P. Equivalently, this is all of the P in spec A such that F of the class P is non-zero. Um, and so basically, this is the locus where F doesn't vanish. Um, he often remark, we're going to write this the way he says that he privately writes this to himself as D F not equals 0. Um,
Hang on 1 second.
he also privately calls this the doesn't vanish set, which I think is kind of funny.
Is the what where F doesn't vanish?
The locus,
Yeah.
but
It's a
yeah,
locus.
we're gonna call this the doesn't vanish set.
Okay.
Um, um, and just as an example of this, spec AF is the subset of spec A where F won't vanish, right?
Yeah.
We've observed that, yeah, so the Zariski topology on the doesn't vanish set corresponds with the Zariski topology on spec AF.
Okay.
Um, so, um, theorem, the set of all distinguished open sets distinguish opens form a base for these risky topology. Now, the definition of a base is one that I don't remember because we spent like 2 minutes on it in topology and said this is just
Yeah.
kind of. But the functional use of a base and the way that we're going to prove that this is a base for the Zariski
Yeah.
topology is that, if we're letting U be in um, spec A, right, and let it
Yeah.
specifically be open, um, want to show that U is a union of distinguished opens. Right, so any open set should be a union of base elements is kind of the criterion that we care about. More specifically, given S contained in A, um, the complement of its vanishing set is the union of polynomials in the subset of the doesn't vanish set. And that this is just kind of true. Like that's just kind of obvious. But then VSC is open in Spec A um, by construction, right? So like literally, that's just it. Um, does that make sense, Garrett?
What?
Does that make sense as a proof?
Yeah. Sorry, I
He
was blowing
calls
my nose real quick.
no, no worries. He calls this one a nifty exercise, and I will say it as a theorem, so I'm going to call it the nifty theorem. Um, let Fi be an A for I in some indexing set J. Um, show that the union of I in J of D Fi is equal to spec A if and only if um, the ideal generated by Fi I in J is equal to A. Or equivalently and very usefully, if there exist AI all but finitely many zero such that the sum I and j of AI Fi equals 1. Whew.
What do you mean by all but finitely many? Because I remember the other day you
Like,
said that that's different from infinite.
like, like there are only finitely many zero. Um, or there
Yeah.
are only finitely many non-zero things.
Yeah. Okay.
But that it doesn't have to be a countable infinity of zeros. So like you could have uncountably many zeros. Like
Okay.
if you let I range over the real numbers as an indexing set, and then you just
Yeah.
picked like three finite points to be non-zero, um, then we're saying that the sum of those non-zero points with Fi is one.
Yeah.
Um, so I think this first one makes the most sense. Right, because
Yeah.
the union of doesn't vanish sets would only be the spec. Like this just seems like a set theory proof, and I'm kind of tired of set theory proofs.
Yeah.
I'm gonna move on from this.
Okay.
Um, I think implication one into two flows. I have no clue where two into three goes.
Yeah.
I have no clue where one into three goes.
Right.
It is nifty, but I'm confused.
Okay.
Yeah. Um. Yeah. Theorem. If spec A is an infinite union of distinguished open sets, union of J in J, um, DFJ. Um, then it is in fact a union of a finite number of these, i.e., there exists a finite J prime in J such that the union of J and J prime of dfj is equal to spec A. And this follows from part 3 of the nifty theorem, right?
Yeah.
Okay. Um, and so then the doesn't vanish set of 0 intersects the doesn't vanish set of G. I said 0, I meant F, is equal to the doesn't vanish set of their product. And I think this makes sense, right?
Yeah.
Like if it's all of the points where F doesn't vanish and all of the points where G doesn't vanish, then multiplying these things together, they have shared roots. So like, yeah. Um, like VF complement, or I guess VF, the vanishings of F intersect the vanishings of G equal to the vanishings of FG. But then taking the complement of all of this that doesn't vanish of F, um, no, this would be the union, because De Morgan's laws. Okay. Does that make sense?
Yes.
All right. So, theorem df is contained in dg if and only if f to the n is in the ideal generated by g for some n greater than or equal to 1 if and only if g is verbal in the localization of a at f. Okay. Right. Okay, this is an interesting one. So let's try the first implication. So 1 implies 2. Well, if the doesn't vanish set of F is contained in, so we're given that set of P in spec A such that F isn't in P, is contained in the set of P in spec A such that G isn't in P, and maybe it's helpful to say Q. Um, or rather, I'm gonna write this the alternative way. Um, F of P is non-zero, and G of Q is non-zero. Um, and so then I have no clue how that implies number two. I know it has something to do with the radical ideal. Like, I think this is saying that F is in the radical ideal of G. But then that means that it vanishes. Hmm. Okay, hold on. He has some exposition. So inside spec A, we have the closed subset of the vanishing of G, which is spec A mod the ideal generated by G. And let's complement DG. So spec A is partitioned into the vanishings of G, which spec A mod G. But then everything else on the outside is DG. Then F is a function on this closed subset VG. Then F on VG vanishes. And so we end up getting like VF. Does that make sense?
Yeah.
Any function vanishing at every point of the spectrum of the ring must be nilpotent. In other words, there exists some n such that f to the n equals 0 in A mod G, i.e. f to the n is congruent to 0 mod g in A, i.e. f to the n is in the ideal of G. And that's the first inclusion. Very proof sketch. Um, yeah. Then for 2 implies 3, implies that G is invertible in the localization at F. Oh, because it's non-zero, like it's non-vanishing. And then in terms of that implying the first part, I think it's that the doesn't vanishes of F must be smaller than the doesn't vanishes of G. Yeah, I think that that works. Proof sketching hella there, but like,
Huh.
I'm gonna say work on, you should work through this on your own because I'm not doing a good job of explaining it.
Okay.
um, as a corollary though, the doesn't vanish set is the empty set if and only if F is in the no radical. Um, okay. So, I don't know. A lot of the stuff in this next chapter is stuff that we've done in Hartshorn,
Okay.
but it's written here in the context of the spectrum, whereas Hartshorn just did it in terms of varieties.
Right.
Um, Naturally, there's a correspondence between the two, and but basically, so section 3.6 is the topological and Noetherian properties of Spec A, and then later schemes. Um, and so like pretty much everything that we proved in Hartshorn chapter 1 is what we're proving here.
Okay.
Um, Give me like 5 minutes to look through this and figure out what is new to us. And then we can tackle the things that are new, and then I'll just write down the things that aren't new.
Okay.
And say, hey, this is true. And then I'll
Yeah.
reference back to lecture 1. So give me like 5 minutes to just look through this. Um,
Okay.
Okay. Are you there, Garrett?
Yep.
All right. So I'm just gonna state a bunch of stuff, and then there's
Okay.
gonna be one exercise that we're gonna skip now, but we're gonna start with next time.
Okay.
And then I think we're good. So definition: the topological space is connected if it can't be written as the disjoint union of two non-empty open sets. Um, and so like just as an example of this, um, if you have a is equal to finitely many of these Cartesian products, then there exists a homeomorphism, which is the I equals 1 to n spec AI homeo to spec A, which sends spec AI, this is the important part, to a distinguished open subset. Um, where Fi doesn't vanish. Um, right, and so this is kind of when we looked in Hartshorne for a while. This was where we talked about like, maximal ideals corresponding to points, and then like, if you have a subset of maximal ideals or prime ideals, then like
Yeah.
you can get these don't vanish sets, and then like, yeah. So then as a remark, spec A is disconnected if and only if A is isomorphic um, to the product of non-zero rings A1, A2. Um, the key idea is to show that both conditions are equivalent to their existing non-zero elements, which are idempotent. So this is if and only if there exists A and A with A squared is equal to A. This condition A is an idempotent element. And so then definition X is irreducible if and only if there do not exist two proper closed subsets A and B with X equal to A union B. And this is something that we've seen before. Um, so just as an example though, uh, C2 is reducible, but A2C is irreducible. Um, okay, so then as a theorem, Um, if A is an integral domain, then spec A is irreducible. And basically, if it's an integral domain, we have no zero divisors. If we have no zero divisors, um, then any proper closed subset is corresponds to prime ideals. Um, and so then open subsets are the DFs, and then you can't union that together.
Yeah.
So now we're down to the tricky exercise that I'm going to pick up with next time. So I'll just define X is quasi-compact if any open cover of X admits a finite subcover, and then if X is also Hausdorff, it is compact, although we don't need to worry about that. Usually the first definition is what people use for
Yeah.
compact, but and then as an example, um, spec A is quasi-compact. Um, and the proof was exercise 3.5c, which is that if spec A is an infinite union of distinguished open sets, then it's a union of a finite number of those. Undistinguished open sets form a base for the topology. So yeah, that makes sense. Um, yeah. So, um, yeah, a point P in X is closed if and only if the subset containing P in X is closed. Um, Hilbert's Null-Stellenschaft, blah 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 blah. A function on a variety over an algebraically closed field is determined by its classical points. Um, Classical points um, are k to the n intersects spec A. Um, yeah, I'll add that as a remark. So functions on X um, equals spec A are determined by their values on closed points. And then, okay, theorem given X and Y in big X. Um, X is a specialization. This is a new word. of y, and y is a generalization of x if and only if x is in the closure of the closed set containing y. And so as an example of this, I don't know if this is a theorem, this is really more of a definition. In A2 over C, which is spec C over XY, the point generated by y minus x squared is a generalization of x minus 2, y minus 4, which corresponds to the point 2 comma 4 in C2. And why is this true? Well, it's that we're moving, the Zariski closure is moving us down a dimension. I'm a little confused. So these both vanish on 2, 4. But then specifically this only vanishes of 2, 4. Oh, duh, it's a specialization. This is a
Yeah.
specialization of the first point. That makes so much sense, actually.
Yeah.
It's specializing it to correspond
Right.
to 2, 4. Whereas this is an entire curve of things that vanish, and it happens to share 2, 4. Okay. And so then this leads to a real theorem. If X is spec A, then Q is a specialization of P if and only if P is contained in Q, where these are prime ideals. P and Q and X, right? And then as a corollary, the vanishing of P is equal to the closure.
Okay.
Um, and then as a definition that results from this, if P of X has the closure, the Zariski closure equal to K, which is a closed subset of spec A equals X, then P is generic. So just as an example of this thing, um, y minus x squared is generic for v of y minus x squared. Um, so this important notion predates Grothendieck. The early 20th century Italian algebraic geometers had a notion of generic points of a variety, by which they meant points with no special properties. So they proved so that anything proved of a generic point was true of almost all of the points of that variety. The modern generic point has the same intuitive meaning. If something is generically or mostly true for the points of an irreducible subset in the sense of being true for a dense open subset, then it's true for the generic point and vice versa. Um, for example, a function has value 0 at the generic point of an irreducible scheme if and only if it has the value 0 at all points. So, like, theorem f evaluated at generic point equals 0. Of an irreducible scheme if and only if f equals 0 on that scheme. Typically, things which are true for generic points hold elsewhere on their variety. The phrase general point does not have the same meaning. So the general point is one point that satisfies such and such a property. Don't confuse the two. I
Okay.
need to blow my nose real quick.
Yeah.
Okay. Um,
I'm sorry, F is 0 on an irreducible what?
Scheme.
Scheme.
Sorry. Yeah.
No, you're good.
Um, so, as a theorem, if P is generic for K closed in spec A, then for every um Q neighborhood of K, P is in the neighborhood. And when we think about sheaves and gluing theorems and how we characterize functions on open subsets, like this makes kind of the idea of generic points make a lot more sense in that like anything that
Yeah.
you're going to prove about a function on an open set or its gluability or its vanishing is going to correspond to its evaluation at the closed point, which is generic.
Yeah.
Um, Yeah. And so we've already talked about this, but there's a natural bijection between points of spec A and irreducible closed subsets of spec A, sending each point to its closure and each irreducible closed subset to its unique generic point. So this is something that we've talked about since day one. It's just kind of with different terminology.
Right.
Um, and so kind of the thrust of this is the theorem that um, every topological space is the union of irreducible components. So like all of this is just our Hartshorne chapter one like stuff. And so like we have Noetherian rings and Noetherian topologies. Um, so like I, I don't want to restate a bunch of stuff that we've already spent time on, but you know, a space X is Noetherian if and only if the descending chain condition holds, if and only if finite generation. Right, so like a topological space is either a finitely generated space or satisfies descending chain condition. Um, basically any of subsets. Um, and so yeah, all of this is stuff that we've proved before. A ring is Noetherian if and only if we have the ascending chain condition of ideals. Um, and this is preserved by quotients and localization. And then we have Hilbert's basis theorem, which we've already talked about, which is that if A is Noetherian, then A over X is Noetherian. And we're kind of just flying through this, right? Like, feel free to
Yeah.
read through this more, but we've already covered this stuff in
Hmm.
Hartshorn 1.1. Um, uh, the same definition holds for A modules. So an A module is Noetherian if it satisfies the ascending chain condition for submodules. The really
Yeah.
interesting theorem that's new in this section is that exactness of m prime to m double prime to 0 um, implies that m prime and m double prime are Noetherian if and only if m is Noetherian. Um, but yeah, and this is kind of the main thrust of this section is like, okay, if you haven't seen Noetherian rings before, then like here we are. Um, okay. So there is one page left for chapter 3.7.
All right.
And I want to go ahead and do that, unless it just turns out to be terrible. So we're going to introduce a notion that in some sense is the inverse to the vanishing set function. So given a subset S, spec A, I of S is functions vanishing on S And so the formal definition will be that I of S is equal to the intersection across P and S of prime ideals P contained in A. Um, when S is not empty. So kind of three observations. Um, I of S is an ideal of A. I is inclusion reversing. Um, and then I of S closure is equal to I of S. Um, and so the attributed exercise to this is that if A is the polynomial ring KXY, S is equal to um, Y and then X comma Y minus 1. Um, consists of the polynomials vanishing on the x-axis, um, or rather, I of S is f in k over xy such that f of x comma 0 is 0 is f of x comma 1. Um, no, 0 comma 1. And then we want to give the generators for this ideal. Um, well, quite simply, this is just y and then 1. We want something that corresponds to 0 comma 1. Um,
Is it not just S? Like the whole thing, like X,
no,
Y minus one?
I don't think so. I think it's a subset. I think it's y minus 1 equals x goes to y minus x minus 1 because that zeroes at 0 comma 1. So y minus x minus 1 generate the ideal. Because that's linear. Um, and then if we really wanted to, we could compute a Gribner basis for this, but I don't think we need to. Um, and then as another exercise, S contained in affine 3 complex space is the union of the three axes xz, yz, and xy. Um, and yeah, yeah. Um, okay. So theorem V I of S is equal to S closure. Um, and then if S is closed in spec A, V of I of S equals S. Um, Note I of S is always radical. Um, Yeah. And so this is exactly what we talked about, I think, when we did do Grosvenor basis stuff, which isn't recorded or on the YouTube channel, so maybe that'll be confusing for anybody random watching this.
Right.
But if you go through some stuff with Grosvenor basis, like this is a pretty standard result. And kind of the main theorem there is that I VI, but for some ideal J, is equal to radical J. Um, and then yeah, so the big theorem, and this is a big deal for Grosvenor basis stuff, is that the vanishing function um, and the ideal of a variety function are inclusion or give bijection between closed subsets. Nope. Of spec A and radical ideals of A. This is occasionally called the Nullstellan shots, right? Like this is equivalent to all of the other Nullstellan shots. Um, okay. So, big theorem is that these things give a bijection from irreducible closed subsets of spec A to prime ideals of A. Um, and so then this gives that in spec A, there's a bijection from points of spec A to irreducible closed subsets of spec A. Hence, each irreducible closed subset has precisely one generic point. So each irreducible closed subset has exactly one generic point. and can be written as the generalization or the generalization, um, which is the Zariski closure of Z. Um, yeah. So I think this is where I want to end. Obviously, there's a lot that we didn't prove today because we've proved it previously, or we've
Yeah,
proved it previously with different wording. But because we went so fast, it might be worth taking some time today, since it sounds like you have some time today, to go
yeah,
through and like make that one-to-one map. Then also on page 88 in the book, there's this kind of dictionary between algebra and geometry that's pretty helpful and just kind of sums up what we've learned in the chapter.
yeah.
And it's all in terms of like Spec A, which is kind of nice.
Right.
Um, yeah, so we'll pick up tomorrow morning with the structure sheaf and definition of general schemes.
All right.
And then that should be a pretty fast chapter. It's actually very
Yeah.
short.
Oh, sounds
Um,
good.
Probably get up to projective schemes tomorrow. And then
Okay.
on Sunday, we can talk about some properties of schemes.
Monday.
Oh, yeah, Monday. Oh, not Monday. I'm going to Universal.
Oh, okay.
Um, Tuesday. Actually, if you can meet Sunday, that might be
I
ideal.
cannot.
Okay.
I have to go to mass real early, and then I'm going to help my dad out with stuff.
Okay, then I might record a lecture on Sunday. Um,
All right.
and then we'll open up on Tuesday with quasi-coherent sheaves. And at this point, we'll get into like big algebraic geometry stuff.
Yeah.
Um, so yeah. All right, I'm gonna go ahead and end the recording.
Okay.
Cool.